Now, the second type of scaling that I want to explain is called horizontal scaling, and it's a little different when it comes to database as compared to servers and other components. It's a little different in databases. So, first let me give you the whole overview. Horizontal scaling is also divided into two parts. One is called replication, and another is called partitioning. Okay, replication. What we are doing here. This is what replication is, and we have discussed it in very deep in another lecture. I think it's episode 3 or 4. I'm not able to recall. I'll put the link in the description. Okay, but what we have to discuss is partitioning. Now, again, partitioning is again divided into two parts. One is functional partitioning. Functional partitioning. That's also called column partitioning. Okay. Other form is called sharding, which is very famous and which is the main topic for today. And it's also called row partitioning. Okay, so let's discuss functional partitioning first. Okay. So what happens in functional partitioning? I hope if you've done, if you've studied computer science in college, right? Even if you've not, I'll explain to you. But if you have studied computer science in college, you must have studied something called normalization, right? In which what we do, we have a database table, which is very redundant. It contains a lot of redundant data, and we divide that table into two parts, and we divide the data actually into two parts so that the table table can so that the redundancy means the replication of duplication of data can be reduced. So one table can be divided into two parts. It's not necessarily dividing every time, but generally dividing is a part of normalization. Okay, so there are a lot of forms: first normal form, second normal form. It is also all of them are part of called functional partitioning. We are dividing. Sorry about that. So we are dividing the particular database or table in that case in terms of its functional requirements. Okay. For example, I'll give you an example. Okay. For example, we have a table in which we have roll number. Okay, roll number, and we have subject or course. You can say course, and then we have fee. Okay. For example, we have 1, 2, 2, 1, 4, 3, 3. Okay, and this is subject C1. This is C2, C4. This is C3, and this is C1, and this is C4. Okay, and we have for C1 we have fee 1000. C2 is 2000. C4 is 3000. Okay, C3 is 4000, C1 is again 1000, and C4 is 3000. Okay, now this is a table and this is a database table. Okay, this table contains a lot of redundant data. You can see the roll number is repeating a lot of times. So specifically, subject is being repeated every time. Okay, so what we can do is that we can divide this into two different tables. One is student table, and one is subject table. Okay, in student table we can normally take this part of the table and we can put it here like this. 1, 2, 2, 1, 3, 3, and again C1, C2, C4, C3, C1, and C4. Sorry, please. It's a little repetitive. So please bear with me. Okay, and we'll create one table for this subject. So we have C1, C2, C3, and C4, and it has its fees 1000, 2000, 4000, and 3000. Okay, now we have divided this table functionally into two parts. Now, if we, for example, if we get a new subject, we don't have to deal with this table alone. We don't have to make changes into student. We don't have to worry about student table and student data anyway. We can just add subject here itself in this table. And if there are a lot of students, extra students enrolling in our courses, we can simply add it in the student table. So we have functionally divided the table, right? So that comes under functional partitioning, and you can see, right, what we are doing, we are dividing it depending upon the columns. So this column is here and this column is here. So it's also called column-wise partitioning. We have divided it in terms of column as well. This is a good example. This is something we generally do whenever our database starts, that starts increasing and our table starts getting very complex. But it has its downsides as well. For example, the very big downside of this particular method is uniformity of data, right? Generally, when we are dividing, it's very much possible that we can have thousands or even 10,000, even 100,000, 100,000 number of students for a particular university, for a particular big university, but subjects can be very less. So the uniformity of data getting divided is not good, right? This particular table is divided into, this particular table will get a lot of columns. Oh, I'm really sorry, guys. Oh. Let's wait for a moment, okay? I hope the power comes back. Yeah, so what happens is that this particular table will get a lot of data, but this particular table will not get data as much as compared to this one. So the uniformity of data is not there. Okay, the uniformity of data divide is not there. So yeah, this can be used for very certain cases where we want to just decomplexify the particular table, or we want to reduce the redundancy of the table. But again, when we are dealing with a lot of users, like millions, billions, this particular strategy also tends to fail later, later points of time, right? Let me check if I've covered everything. So now the solution to this comes in form of sharding, which is our main topic for today. And just let me erase this, then we'll discuss it. Okay. Now, what happens in sharding is that we do not divide data in terms of its function. We generally divide data. We generally do not even denormalize the table. We keep the table as same, and we just divide data depending upon the particular, if I say the quantity of data we have for the particular table. I'll explain you in a minute. Okay. Let me draw the same table. I have erased it, but yeah, the same could have been used. No issues. Roll number, codes, and fee. Okay. We have one, two. Let's make it uniform. And we have codes C1, C3, C2, C4, C1, C4, 1000, 3000, 4000. It's a little different. It's not exactly the same data, but yeah, let's assume it. Okay. This is 2000, this is 1000, and this is 2000. Okay. Now, instead of dividing this data into two tables and dividing it in terms of rows, what we'll do, we'll keep this data as it is, and as the number of students increase, for example, we have 4, 5, 6, and it's increasing. We'll not divide it in terms of table. We'll just divide it in terms of whatever number of roll numbers you're getting. So, for example, 1 to 4 will be in one part. 5 to 8 will be one part, and 8 to, just like that, right? Depending upon the number of shards, number of parts. Shards generally is called the parts. Shards means one database is divided into multiple parts. Okay, each part is called a shard. Okay. So we can divide data in terms of its quantity, not its functionality, and we can store each of this quantity into one database. Now, generally, it's not necessarily that we store all of these in different databases. One shard can, multiple shards can be in a single database also. We can decide, right? For example, what particular shard is getting a lot of data, so we can keep it in one database. But few shards are not getting a lot of data, so we can put it in one database. We can define that strategy. Now, how I have come to the conclusion that this 4 will be in one part and this 4 will be in other part. And like how I decided that only the partitioning will be only according to the four number, according to first four and then the next four. There is something called a partition key. If you have heard about that term, right? It's called partition key, or sharding key also is called sharding key. Sharding key is a particular row in the table using which we define a function, and that function can decide depending upon the particular row which particular shard the data will go into. I'll give you an example. Okay, for example, my function here is a hash function, and it's called roll number percent, the number of shards we have. For example, if we have 4 shards, I'll do 4. This is number of shards. Okay, so for roll number 1 it will be 1% 4, which is equals to 1. So roll number 1 will go to shard 1. Okay, 1. Roll number 2, percent 4 is 2. It will go to shard 2. Roll number 3, it will go to shard 3. 4, it will go to shard 4. Similarly, again, 5 comes, 5, it will go to shard 1 again. Number 5 is 6, it will go to shard 2. So this particular hash function is, you can see, uniformly dividing our data, whatever is coming into it. So this is a good hash function for a very simple use case. It's not usable in all of the cases when you'll be dealing with a very huge amount of data. There are a lot of hash functions you can define specifically for your use case. But this is a good hash function for this particular data that we're getting. It is uniformly dividing the data into all the 4 shards that we have, right? Now, one of the very main benefits of this particular strategy is that we are actually achieving what we call horizontal scaling, right? We can add as much number of shards as we want, and we can modify our particular partition key and we have a partition function, so that it can incorporate different kind of data that we have. So the actual use of horizontal partitioning we are getting here. So it's a very much benefit. So sharding is the most widely. It's not the only solution that we have. It's not the very best. It's not like that we use it everywhere. But generally, for a very large use case, whenever we're dealing with very large number of data, very large number of users, sharding is a very good practice, and it's used very widely. Okay. Now, if there are a lot of benefits of sharding, then there are a lot of downsides also. The very first downside is that it's called rejoining of data. For example, I want the data for this particular use case, right? I want data of user 1, user 1, user 6, user 7. So if there is a query, the data that we want is spread across different charts. We have to query all of the shards at once. So for a single request, our request will transform into the number of shards we have. The overhead will increase for that. Again, when we will fetch all of the data, we have to perform a join operation to join that data again. It's again an overhead for the particular database server, right? So this is one of the issues, that the data is, since the data is divided, we have to perform some kind of operation to join the data back in order to make it usable. Second issue, it's called a celebrity problem. It's a very famous problem. It's seen in a lot of components, but here we can see it here in sharding also. So for example, I have this database which stores data for very famous scientists. This is for celebrities. This is for politicians. This is for something. Okay. Now, it's very much possible that the database for celebrity will be very much loaded, because on the internet, most of the searches goes in not for scientists, not for politicians, but for celebrities. So most of the queries will come for this particular shard only, and this will be loaded up more as compared to this all of the other shards. So again, right, the main goal of our main goal of dividing data, so that we can divide the number of we can divide the requests coming into our database, and we can reduce the load, is technically not achieved, because this particular part of the database is getting access every time. So to avoid that, we have to define our partition key and our sharding strategy very, very carefully. That's why it's very important to define our sharding strategy and what partition key we are choosing it very specifically, as it can lead to this particular problem. It's called celebrity problem, right? Point number 3, let me check. Third point is again same as for what we have discussed in first functional partitioning, right? If we do not choose the partitioning key very carefully, what could happen is that the uniform, like we have seen in earlier example that our data was getting divided uniformly. But if we have not chosen a partition key very carefully, what it would have happened that one shard could receive a lot of data, and we could have seen the same, in a non-uniformity of data as we saw in functional partitioning, right? We saw that a single table or a single part was getting a lot of data and the other part was not getting the same amount of data. Same we can see here as well. If a bad partitioning key or an or the partitioning function that we use is not very carefully designed. So yeah, this was sharding, and this was horizontal partitioning specifically. I do not see anything else that we can fix here. Yeah, I think that is it. Thank you very much.